Okay, so why don't we do this practice problem? We have this implicit curve, x squared y squared plus xy is equal to 2, and this is the graph of that. And the question is asking to find all points on this curve where the slope of the tangent line is -1. So first of all, just as a review for tangents, do you know which quadrants these points that the slope is -1 possibly exists? Like, if it does exist, which quadrants do you think it would be in? So remember, quadrant, I mean like quadrant 1, quadrant 2. Yeah, you expect it, if these points do exist where the slope is -1, only possible choices are this quadrant and this quadrant. Right? In this quadrant, the derivative is positive, right? And same here. But over here, it's negative. Do you expect the derivative ever to be 0? Exactly 0? No. Yeah, so, but it's going to be maybe close to 0. Close to 0 as you go up to infinity or to -infinity. Where does the derivative never exist? So implicitly, where does the derivative not exist? What point can I not draw a tangent line? For what x value can I not draw a tangent line? Is there any point? I think there is one. -1, well, that's like maybe around here, right? Yeah, 0. Yeah, so for x values. So yeah, so right here at 0, there's no tangent line. Right, it's an asymptote. So you expect the derivative not to exist. So you expect d dx of 0, it does not exist. So just some preliminary observation. So when we do the derivative, we'll expect this thing the derivative not to exist. Okay. First of all, do you see why 0 is not an x value of this curve based on this formula? Why is 0 not an x value that agrees? It'd be obvious, but why is 0 never an x value on this graph? Y is y value. Yeah. Yeah, if you plug in x equals 0 here, you'll get 0 equals 2. Similarly, if you plug in y equals 0, you get y equals 2. So that's further evidence to why this graph might be okay, right? You can't plug in an x value because then that's a vertical asymptote. You can't plug a y value because that's the horizontal asymptote. There's no x-intercept here. Okay, so let's actually do it. One sec. This happens sometimes. Okay, how do I get rid of this? All right. Okay, good. All right, so let's do the derivative. So how do you find the derivative of, or implicit derivative of an implicit function? what's your first step? What's your first step? To find the derivative of an implicit function. Yeah, just take the derivative on both sides. Yeah, and then your last step would be to solve for dy dx. Okay, so these are always your two steps with implicit differentiation. Okay, so let's do it. Okay, while I'm writing this out, can someone tell me the derivative of the first thing? And by the way, you can speak if you would rather speak. Oh, is someone... Oh, I don't hear it. I don't hear it. Okay. Oh, for some reason, I can't hear. Oh, was someone speaking? Did I not hear them? Right, well, if you try speaking, let me know, because I didn't hear if someone did speak. All right, so... Oh, sorry. Yeah, sorry if you missed that. I changed. I made you able to speak. Just thought it would be better interaction. All right, so let's do the derivative of this one. How do you find the derivative of x squared y squared? Yeah, it's a product rule. So the derivative of the first is 2x and then times y squared. And then you have x squared times the derivative of y squared. Oops. And then yes, which is 2y dy dx. Good. And then what's the derivative of xy? If you could do this one, I think you could do this one too. So it's derivative of x times y plus x times the derivative of y. Yeah, good. And then the derivative of a constant is 0. Okay, so solving for dy dx, let's have 2x squared y dy dx plus x dy dx. And this is equal to negative 2xy squared minus y. All right, so solving for dy dx, we have dy dx is equal to negative 2xy squared minus y over 2x squared y plus x. Okay, everyone agree with that? All right, good. All right, so now what does the question ask? First of all, actually, let's think about our analysis. Can you plug in x equals 0 here? What happens when you plug in x equals 0? What do you get? Yeah, it would be undefined. You get negative y over 0. Yeah, so this is undefined. And that satisfies our picture, right? At x equals 0, there's nothing there. How about y equals 0? Well, there is no y equals 0, right? Right, there's no x-intercept. Probably do some other things where you have, you could plug in like a, b, negative a, b, negative a, negative b, and like a, negative b, like to check for the quadrants, but we don't have to do that. So anyway, the goal here is to find all points such that the slope is negative 1. Okay, so what does that mean we do? So yeah, so what do we do? So we want to find all points at the slope of the tangent line is negative 1, and this is our derivative. So what do you think our next step would be? Yep, set the derivative to negative 1, because the slope of the tangent line is precisely the derivative. Okay, so we have negative 1 is equal to 2xy squared minus y over 2x squared y plus x. Okay. So let's maybe simplify this. So I have negative 2x squared y plus, minus x is equal to 2xy squared minus y. And let's just see how your math intuition is. How would you think to continue? You're going to find all pairs xy such that this equation is true. So it's maybe a bit tricky, but what's always your kind of intuition to solve for x and y? Like, if that's too hard of a question, like if you only had one variable, what would your intuition be? Yeah, true, x is a common factor in the left. However, we couldn't really do much with it. But that's good to think about factoring, because that's something we will want to do. Yeah, as you would with any type of one variable equation, you'd always want to put all the variables on one side and then maybe factor. Because the big thing is these squared terms always pose a problem, right? You can't like just set y equals or x equals. So a good strategy is to just set all things on one side. So let's do that. So 2x squared y and 2xy squared plus x minus y. Okay. Oh, the top is, this is a minus. So this is a minus. Okay. Okay, so now that we've done that, can you see a factorization? Even though there's more than one variable, things can still factor. Yeah. So in this first term, there's a common factor of 2xy. So then you get, what do you get? You get x squared, or no, you get x minus y. Oh, I see. So if you pulled out this x as well, you'd be stuck with having extra minus y at the end there. I see the 1 plus 2xy, like you, would you combine these two? And then maybe combine these two? That might actually also work. I just thought this one might be an easier approach. Shouldn't it also be where? 2xy squared? That's here, right? This is the 2xy squared. And this is the 2x squared y. And this is grouped this way. And yes, they're both positive. Yeah, so this is factoring by grouping. So if you're uncomfortable with that, it'd be good to review that. Essentially, you're grouping the two expressions that have a common factor. Oh, sorry. What should be plus? This one? This one? It's minus here. Oh, yeah, this should be minus. Sorry, yeah, that was wrong. Yeah. Sorry, yeah. That was incorrect. So I miswrote it from up here as minus. Yeah, this wouldn't work if that were plus, right? Then you couldn't factor it. Yeah, that was my mistake from before. Okay, so now this is all factorable. Yeah, so be careful with the parentheses. 2xy plus 1, and then x minus y. But yeah. Okay, so what does this mean? Is that dy dx equals -1 for all xy that satisfy 2xy plus 1 is equal to 0, or x minus y is equal to 0. Can someone say why that's true? This is just, I mean, that's what you do when you're factoring, right? If you have two factors whose product is 0, that means that one of them is 0 or the other one is 0. Yeah, so either 2xy is equal to -1 or x is equal to y. However, I can't have x and y equal 0, right? Because that doesn't agree with our original graph. So speaking of which, we have to come back to our original graph. So it's an x squared y squared plus xy equals 2. X squared y squared plus xy is equal to 2. Okay, so we know that the derivative is -1 if either of these cases happen. So let's do them. Let's do this one first. That looks easier. Suppose x is equal to y. What equation do you get when x is equal to y? So in the graph, what are all points where x is equal to y? That's what it's asking. So remember what this equation means. This is all points x, y such that this thing is equal to 2. So what happens when x equals y? So that means x squared plus xx equals 2, right? Because x equals y. That's all. Okay, how do you solve this equation? X to the fourth plus x squared is equal to 2. How do you solve that? And how do you solve it not by guessing? You could do that, but remember you have to find all solutions. You do x squared, again, the intuition is right to do factoring, but this doesn't tell you anything, right? You can't do anything with that. But what's a step you should make before that in order to do that? But you are right, 1 is a correct solution, but the goal is to find all points. So you can't really guess every number in the universe. So you do have to factor, but not we have to do something to this equation first before we factor. Yep, always set everything equal to 0. Okay, good. All right, so how do you solve that? Can you factor that? Can you factor this equation? Yeah. Maybe. Do you remember? Yeah, it's a quadratic. So if you could do it like straight from here, but if you like the intermediary step, you can set let u equal x squared, and then you have u squared plus u minus 2 is equal to 0. So maybe that's easier to see how it's factorable. So what's that factorization? It's a great question because there's a lot of like important steps that we need to remember how to do. Yeah, this is substitution. You don't have to use substitution. You can go straight from x squared with the factors, but yeah, so anyone have the factors? What are they? Yeah, so but u, right, because we have u here. So u plus 2 and then u minus 1. No, that's fine. But it's important to have just make sure that you have it different from this x. So that means u is equal to negative 2 and u is equal to 1. So this means that x squared is equal to negative 2 and x squared is equal to 1. Right, this is bringing back in u equals x squared. So what's the answer? What are the x values? How about this one? how do you solve this one? What are the x values there? Positive or negative 1, I agree. But think about this one some more. How do you solve this? Not radical 2. Look closer at what's underneath that radical. Okay, let's try square rooting. What happens when you square root? What is that? Yeah, who knows what that is? Right, there, it's an imaginary number. That's we live in the real land, not imaginary land. So it's just x equals plus or minus 1. So what are the xy values? Right, this is all set up to be, what case was this? This was case x equals y. So xy values are 1 and 1, 1 and negative 1. Okay, sorry, negative 1, negative 1. All right, any questions on that? And this kind of makes sense in our picture, right? If we go back all the way up here, these were kind of one, this is like 1, 1, and this was like negative 1, negative 1. So it satisfies our guess, right? Well, they're in the first and the third quadrant, and they kind of look great. All right, yeah, so questions on that case? So we still have to do the other case, right? So this might be something. Okay, so I probably want to use substitution here, right? So what variable do you want to solve for? To make it easier, you could just say xy is equal to, actually you can just do that. If xy is equal to negative 1/2, what's x squared y squared equal to? Yeah, 1/4, right? X squared y squared, you know, is the same as xy squared. So this would equal to 1/4. Okay, so if you plug that into the equation here, you get 1/4 minus 1/2 is equal to 2. So what is that, negative 3/4? Oh no, that's negative 1/4, right? Negative 1/4 is equal to 2. Huh? What does that mean? It is not a valid case. Good. That doesn't mean you did something wrong. That just means that this case is not valid. Not valid. That's good. So in other words, 2xy is never equal to negative 1 in this graph. So that means that this is our only solution. All right, so good application of, so notice, I mean, just, we stopped calculus here, I guess, right? Calculus, and maybe we use calculus to say what that means, but the rest of it was algebra. So again, I think the most important thing is just to make sure you're comfortable with algebra, right? And the calculus is not many steps. Anyway, any questions on this? Okay, so today we're going to talk about related rates. And how I like to talk about related rates is just to do problems and talk it out. Because I think the intuition is a lot more important than, coming up with an algorithm. But so if you intuitively understand it, then it just makes sense how to set it up. Okay, so this is a good question. So you have a cylindrical tank that has a radius of 5 meters, and it's being filled with water at a rate of 3 meters cubed per minute. So the question is, how fast is the height of the water increasing? So there's a lot of derivative words here, right? Right, the derivative is like a velocity, right? It's a rate of change. So you imagine the derivative would appear somewhere here. So first of all, what is changing? As time increases, what is changing? Someone say? The amount of water in the tank, yeah. So in other words, the volume of the tank. So what does this mean? As time is changing, how is volume changing? That's exactly a derivative, right? So let's do it. So we need to find an expression of volume of a cylinder. Anyone remember the volume of a cylinder? Yeah, pi r squared times height. And if you don't remember that formula, it's not a hard one to forget. The radius, so the area of the circle is pi r squared. So how I like to imagine it is like, I always think of CDs, but that's not really a thing. Those aren't really a thing anymore. But if you stack CDs up, the number of CDs is the height. And the area of each CD is pi r squared. So kind of with the net material, you could say, is pi r squared times height is the volume. So I need a different analogy nowadays because we don't do CDs anymore. But yes, yeah, so that's kind of how I remember the volume of a cylinder. Okay, so that's what we have. We have volume is equal to pi r squared times height. Okay, so now, as volume is changing, as time is changing, volume is changing, right? So what does that mean? That perhaps there is a function of volume or the function of time that says at what point in time, what is the volume? So what could this be an expression of? Well, it's pi, however r is changing, may not change, and however the height is changing, right? Do you agree that if r changes and h changes, that means the volume will change? So this is a valid expression for what the volume of a changing volume of cylinder. This would be your formula. It's related to how the radius is changing and how the height is changing. Is that an okay statement? So this is the changing volume over time. Any questions about that? And does that make sense? So our volume is changing because we're filling it up with water. Is there an expression here that doesn't change? When you fill up a cylinder with water, what does not change? So of all these cases, what is the thing that's remaining fixed? The height is the changing thing, right? As you fill it up with water, right, the height of the water is increasing. Sorry. Yeah, the area of the circle. So, or the radius, right? Between all these states, the thing that's remaining fixed is the radius of all these circles. Or even, I don't have to draw all these cases, just the base circle, right, is the only radius that we care about. Yeah, the radius is not changing. So the radius is a constant function. But h is changing, right? This is not constant. It's helpful to establish this before even talking about the derivative because it makes it easier. Okay, so now let's kind of look at our statement again. Okay, so cylindrical tank with radius 5 meters. Okay, so immediately we can plug in 5 for r of t. So the radius is not changing, right? This is not an expanding cylindrical tank. So now it's being filled with water at a rate of 3 meters cubed per minute. So what do you think that word means? What math word is being filled at a rate of 3 meters cubed per minute? What math word do you think that is? Anyone? What does that mean? We don't necessarily know that. Is h changing? I mean, it is, but literally, what does it mean? It's being filled with water at a rate of, what does 3 meters cubed per minute mean? How is it changing? It's not directly saying how the height is changing, but what is changing. Yeah, this is precisely the derivative of the volume. That was the word I was looking for, volume. So with meters cubed per minute, if you can't see that, right? The meters cubed per minute, that tells you volume, right? And the rate tells you the derivative. So it's a constant rate. So we know that dv dt is always 3. So we need to find the derivative of our expression for volume. Okay, what is that? All right, what's the derivative of this expression here? Remember, h is a function of t. You could replace t with x and you'd get like the same thing. Well, what's one thing we can do with this derivative? I mean, I'm looking for a simple answer. It's not complicated. We don't know what the derivative is, but so it's literally just 25 pi h prime of t, or dh dt. That's all, right? The derivative, right? The derivative of f of x is the derivative of f. So just solve for h, dh dt. Yeah. So there wasn't much to do here once we found the derivative, because it's a constant. This is constant, constantly increasing at a fixed rate. Okay, questions about this one? We'll do more. This is kind of a good one to start with. Okay, if not. Okay, we have a square, and each side of the square is increasing at a rate of 6 centimeters per second. So the question's asking, at what rate is the area of the square increasing at a specific time when the area is 16 centimeters squared? So what I always recommend with these word problems is to draw it. So you have a square that's increasing at a rate of 6 centimeters per second, each side. Now, just a silly question: why does each side need to increase at the same rate? Right. If one side was increasing faster, right, then you get like a rectangle. Yeah. So each side is increasing at the same rate. Okay, now it's asking, at what rate is the area of the square increasing when the area is 16 centimeters squared? Okay, so let's ask some math language. At what rate is the area of the square increasing? What math word does that mean? What math word is that? Yeah, of what? So definitely derivative, but what is the thing you're taking the derivative of? The area function, yeah. Okay, now, what math word does this mean? Each side of the square is increasing at a rate of 6 centimeters per second. What math word is that? Also derivative, yes. Of what? Yes, length of the side function. Length of side function. Okay, good. So if we know these two things, what we want to find is the derivative of the area. So what is the area function? Yeah, I like S for side, but you can use X. Okay, so that means if we just put a T everywhere, then this is the changing area function. Okay, so what's the derivative? We need to find the derivative of a of t. Okay, what is the derivative? What's the derivative of s of t squared? Good, yeah. This is like a chain rule, right? You have the function s of t, and you have the square function. So I like to think of it also like implicit differentiation. Like this is what you would do with implicit differentiation. ds dt. But we know what ds dt is, right? What is ds dt? Yeah, I put this color for a reason, right? We know it's increasing at a fixed rate as 6 centimeters per second. So dA dt is equal to 12 s of t. Okay, now what? We want to find at what rate is the area of the square increasing when the area is 16 centimeters squared. Okay, so that's the area function. It's when, so that's why it's a of t. Yeah, so that's it. When the area is 16 centimeters squared. So it's when a of t is 16, solve for t. Okay, so let's do that. A of t is equal to 16 is equal to st squared. Okay, so square root 4 is equal to s of t. Do you know what s of t is? We know what the derivative is, right? So what does that mean, s of t? Yeah, sorry. Yeah, never mind. Yeah, we know, sorry, my bad. Yes, we know that when area is 16, s of t is 4. Right, so dA dt is equal to 12 times 4. Thank you, yeah, is equal to 48. So yeah, we don't know what time is, and that's okay. I mean, technically, the s of t would be 6t plus something. But yeah, we don't know what the plus something is, so we can't solve for t. Yeah. So we actually could maybe should have said is a of t naught or something is equal to 16, and then this is equal to some s of t naught. Okay, any questions on that? Yeah, so just to reiterate, we don't care about when, at literally what time, the area is 16 centimeters squared, because we have all the information from the derivative and from just the area function. All right, questions on this one? All right. Okay, this is a fun one. Okay, you have two cars that start moving from the same point. One travels south at 16 miles per hour, and one travels west at 25 miles per hour. The question is, at what rate is the distance between the cars increasing 2 hours later? Okay, so again, let's underline some things and say what the math equivalent is. Okay. What math word is that? One travels south at 60 miles per hour. The south isn't the important part. Hint. Yeah, well, it's just literally speed, right? So it's a function of time, but it gives you distance, right? So it's a derivative, right? It's as time is changing, distance from start of car A, let's call it. So it's just speed. But just to be pedantic, let's just say distance of start with respect to time. Okay, so similarly, this is d dt of the distance of car B. Okay, then what is this language? What rate is the distance between the two cars increasing 2 hours later? Or we can ignore the 2 hours later for now. So it's definitely a derivative, but what is it of? I mean, it says it right there. Yeah, distance between car A and car B. Okay, then we'll get to this when we get there. Okay, so let's draw the picture. This is the start, and then car A travels at 60 miles per hour. Let's say they stop here at 2 hours later. Car B is traveling west at 25 miles per hour. And then let's say stops here 2 hours later. So the question is, at every point in time, right, there is some distance between the two cars. And as time is increasing, this distance is increasing. At some rate. We don't know what the rate is. It could be a changing rate or it could be constant. We don't know. So the question is, at this point in time, what is d dt of Yeah, we want to find that, the derivative of how fast the cars are getting further apart from each other. Does the picture make sense? So all those lines represent different points in time. And the distance between the two cars at any point in time. And this line at the end represents the distance 2 hours later. Questions? What geometric shape does this make? All these specific states in time, what geometric shape is this? I mean, the triangle, but how about specifically? Yeah, it's a right triangle. Why do you know it's right? Yeah, but I mean, reading this, how would you say it's a 90-degree angle? It's important to see that. I know it's maybe obvious, yeah. Yeah, it's due south, due west is 90 degrees. So that's very key. So we can't do our next step if we don't have that statement. Okay, so big question. What is the distance between car A and car B? At some point in time. Yeah, the hypotenuse. So just to make this a little bit, let's call this function a of t, and let's call this function b of t. And let's call this function c of t. Right, so the distance between any 2 points in time is the hypotenuse of the right triangle that's always formed. Right, at every point in time, there's always a right triangle, so that's very important. No matter what the position of the car is, right, any line you draw here to here will always make a right triangle, right, because this is always right. So how do you measure the hypotenuse of a triangle with respect to its sides? Pythagorean theorem, yeah. So whatever the distance between the two cars is, its squared is equal to a of t squared plus b of t squared. Okay, so now we can do calculus. Okay, so what's the derivative? How do you find the derivative of this? We'll take a break after this question. Yeah, just a bunch of chain rules. So this is similar to our square question, right? So they'll all look the same. Right, so this is 2 c of t dc to t. And this is 2 a of t dA dt. And then plus 2 b of t dB dt. Okay, what can we do? Can we do anything? Simplify this? Right, what is the goal again? We want to find this at 2 hours later. That's the goal. So how can we simplify this expression? Do we know anything? Well, what's the obvious one that you can do? Yeah, we know dA dt and dB dt. What are those? Yeah, dA dt is 60, and dB dt is 25. So even before then, though, we can get rid of these 2's, right? These all have a factor of 2. Okay, so what does this mean? We have C of t dc dt is equal to 60 A of t plus 25 B of t. So what is the goal? What is dc dt 2 hours later? So we plug in 2. Do we know what these values are? Do you know A of 2, B of 2, C of 2? Yeah, what are they? Yep. So if car A is traveling 60 miles per hour and they travel for 2 hours, well, travel 120 miles. Car B is traveling 25 miles per hour for 2 hours, 50 hours. Okay, do we know what C of 2 is? Yes, Pythagorean theorem. C of 2 is A of 2 squared plus B of 2 squared square root. Okay, so let's express that. So whatever that is, square root of 120 squared plus 50 squared dc dt is equal to 120 times 60 plus 25 times 50. Sorry, not 120. A of 2 is 120 squared plus 50 squared. Okay. Let's see, it's easier to solve maybe. Okay, well, one thing you can do, this is 12 times 10 squared. Five times 10 squared. So it's that, pull out a 10, you get 12 squared plus 5 squared. So it's 144 plus 25. Oh, it's 130? Yeah, okay, then that's 169, which is 13. Cool, 130. Yeah. This is human calculator. Okay, so this is 130, yeah. So 130 dc dt is equal to 120 times 60 plus 25 times 50 So you can calculator it. That's a 25. I'm not sure if I can simplify that. It's whatever 120 times 6 is. What is that, 125? 125. Yeah, 13. I think that's as far as we can go. Yeah, so whatever that is a fraction. That's your dc dt at that point in time. All right, any questions? What is this, 780 plus 125 over 13? How can we take what, the 10 here? Oh, I'm just, yeah, simplifying it. These both have a factor of 10 squared. So if you take it out, it's square. You have a square root of 10 squared. If you factor out the 10 squared, and then that's 10. So this step here is 10 squared, 12 squared plus 5 squared, and then it's square root of 10 squared, square root of 12 squared plus 5 squared. Wouldn't it be 2.5 on the right if you pull out the 10? I pulled out a 10 from the 50. So yeah, just 110. Yeah. Yeah, so whatever that is, 905 for 13. Anyway, so yeah, so simplify from there, and that's your derivative. All right, so any questions on this? So again, where was the calculus? It was this step. Or no, it was step up here. Here was the calculus, right? The rest was just, computation. So with these word problems, it's all about the setup, right? How do you set up the equation that you need to take the derivative of? And then once you do that, then it's just a normal word problem. Okay, so let's take like a 5-minute break. So we'll meet back around 8:50, and I'll have this one while we take a break. So work on that, or take a break. If you have any questions, let me know. All right, about 5 minutes. Okay, let's start tackling this question. Okay, so the altitude of a triangle, it's increasing at a rate of 1 centimeter per minute, and the area of the triangle is increasing at a rate of 2 centimeters squared per minute. And the question is, at what rate is the base of the triangle changing? And the altitude is 10 centimeters, and the area is 100 centimeters. Okay, so let's do the similar thing. So the things I underlined, and I recommend you underline, similarly, by the way, when you do these problems, because I think it helps just to understand, what everything in the sentence means. So how about the first statement? Altitude of the triangle increasing at a rate of, what math word is that? So I'm gonna let h be altitude for height. Yes, derivative of what? Of h of t, yeah. Okay, how about the area of the triangle increasing at a rate of 2 centimeters squared per minute? Oh, so, and this is fixed, right? Is constant. 1 centimeter per minute. How about the blue? Area of the triangle increasing at a rate of 2 centimeters per minute? So this is also constant. And how about the third one? So is this constant? Yeah, we don't know, right? That's what we're going to try to find out, right? So the thing is, when the altitude is 10 centimeters and 100 centimeters, the area, this might suggest, it may not just be fixed, a fixed rate. Okay, so what do we have to do? Yeah, what do we do? So that's all the info. So how do we get this information? Yeah, we need to work with the area function. We have the derivative area is constantly 2, and we know what area is, so probably have to use the area function. So we know what the area function of the triangle is. It's 1/2 base times height. Okay, so what is the derivative of that? So by the way, this is why I like to put the of t's, because yes, this is a product rule. Right? If you didn't put the of t's, you might think they're constants, which they're not. Yes, we need the product rule. So let's do b of t dh dt plus h of t db dt. And this is equal to dA dt. Okay, so what things do we know? Do we know any of these values? We actually know a lot of values. There's maybe one that we'll have to find, but yeah. We don't know dB dt, but we do know dH dt is 1. We know dA dt, which is 2. And we know one more thing. Okay, so actually, in general, this is what the derivative looks like. So 2 is equal to 1/2 b of t plus h of t dB dt. So now we want to care about at time t naught. At time t naught, when h is 10 and a is 100. That's what we want, right? The goal is to find what this is. If we look at our question again, what this is when h equals 10 and a is equal to 100. Okay, so what other piece or pieces of information can we figure out from this? So can I find what's h of t naught? Well, it's right there. It's 10. And the only other thing that we don't know is b. What is b of t naught? Ah, yes, we do. We know that a of t naught is equal to 1/2 h of t naught, b of t naught. We know a of t naught is 100. We know h of t naught is 10, and we don't know b of t naught. But we can figure it out. And what is that, 20? Yeah, 20 is equal to b of t. The questions on how we got that? So this is at time t naught. Questions? Okay. So just solve now. Okay. So we have -8/5, which is interesting, right? So if you have this scenario, that means the height is increasing. So we have the height of the triangle is increasing, but the base is decreasing. But it's increasing in such a way that the area is increasing. So total area of the triangle. Okay, so questions about that? Okay, so let's do another one. Okay. So a particle is moving along a curve, y equals radical x. And as the particle passes through the point 4, 2, its x-coordinate increases at a rate of 3 centimeters per second. So the question is, how fast is the distance from the particle to the origin changing at this instant? Okay, so I think the first thing we could do is just graph it first. We know what these things look like, and then we can start underlining some key clauses. Okay, this is square root of x, something like that. And we have a particle that's moving along the curve. We don't know how fast it's going, but we do know that at 0.42, we know that the x speed is increasing. Oh, I won't write everything out, but it's going to be 3 centimeters per second. Okay, so here are the probably the most key words here. X coordinate increases at a rate of 3 centimeters per second. And how fast is the distance to the origin? Okay, so let's think about distances from the origin. So that's these lines. Right? These lines are increasing as the particle is moving. So the question is, what's happening here? What is d? Oh, we don't know this, right? how much is this changing? Okay, so what is the blue? Okay, what is that as a math word? Its x-coordinate increase at a rate of 3 centimeters per second. What a math symbol can we express for that? Anyone? What is that? Increases rate of is always what? What have we been doing for about a month? So the units are actually important here. Well, okay, that's ddt. This is a derivative, obviously. Rate increases at a rate of. What is the thing that's changing? X, yeah. Right? X doesn't need to be the thing you take the derivative of. We're taking the derivative of time. How is X changing? How is X changing with respect to how time is changing? So technically, right, X is actually a function of time. Pick any point in time, there's an X value. So X of t is the X value at some point in time. What is d dt of X? What is dx dt? Yeah, it's fixed. Fixed to be 3 centimeters per second. This is a fixed rate. That's important. Okay, so what is the next underlined sentence mean? What math language can we use there? How fast is the distance from the particle to the origin changing? Maybe we don't need at this instant. So again, it's ddt. And I'm asking this every single time, but it's a good habit. But what's changing? What is the varying thing? Yeah, distance to the origin. So it's distance between point and origin. Okay, so what is the distance between the point and the origin? Distance between point xy and origin. 0, 0. Right? The idea here is that, well, if we want to find the distance, how fast the distance between the point and the origin is increasing, well, I probably need a formula for the distance to the origin. What is a formula for the distance to the origin? Yep, that's it. Just distance between 2 points formula. Yeah. So the distance between the 2 points is the square root of, right, it's x1 minus x0 squared plus y1 minus y0 squared. Okay, so yeah, so x0 and y0 is 0. 0, 0. So then this just simplifies nicely to x1 squared plus y1 squared. By the way, you could do this if it wasn't at the origin. If it was out here or something, you could still do this, but you would have this extra term here. So just be aware of that. Okay, so these are functions, right? So d of t is our function square root of x of t squared, which we know something about, and y of t squared, which you don't maybe don't know much about. But I think we do. Okay, so let's take the derivative. What's dt? It's kind of awkward. dt? dt? How do you take the derivative of this function? How do you take the derivative of x of t squared, the square root of x of t squared plus y of t squared? Chain rule, yeah. So this is, if you don't like square roots, just remember they are just an exponent. So this is 1/2 x of t squared plus y of t squared to the negative 1/2. And then what else do I have to write? What's the next part of the chain rule? So that was the derivative of the first, the outermost composite. And then how do I finish the derivative? You don't have to type the whole thing out. Just yeah. So it would be 2x of t dx dt plus 2y of t dy dt. Okay. All right. Do we know any of these things? What things do we know? If you want to go right to t naught, that's also, yeah, x of dx dt is, a different color, is 3, because we were given that. Okay, anything else? How about at t naught? Do we know anything at t naught? Or t naught is the place that I care about. Not 0, right? Where do I care about? Where am I looking for the derivative? Yeah, 4, 2. So we know that x of t naught is 4. Y of t naught is 2. Well, these are squareds, right? So this is 4. This is 2. So the only thing we don't know is dy dt. But I think we do. Can you figure out dy dt? What's one thing we haven't addressed? Look at the question again. What's the one thing we haven't used? The function, yeah. What is the function? Y is equal to square root of x. So y of t is square root of x of t. So dy dt is the square root of this. So that's 1 over square root of x of t, x prime of t, or dx dt, whatever notation I've been using. Okay, so let's plug it in. So we have d dt, or this notation probably looks ugly. Let's use d prime. D prime of t. So 1 over radical 2 radical 20. That's this one here. And then, so 24 plus 4. And then what happens when you plug in the point that we want? T naught was 4, 2, right? So this is 1 over square root of 4. And then dx dt was 3. So 1 over 2 radical 20. 24 plus, so this is 2, makes 6. So 30 over 2 radical 20, and that's 15. So if you wanted to rationalize, like good students, you have that, which simplifies down to, what is that? 3 radical 20 over 4. Okay, and this is at some point t. Okay, questions about this? So notice a lot of these, we don't actually care about the time, right? We're not solving for the time because we don't know, the time itself, how many seconds have passed. We can just look directly at the point itself. Okay, questions about this one? Okay, so let's do one more. We may not have time for it, but we can start it. This is supposed to be increasing in difficulty, so this one I thought was the hardest of the bunch. Okay, so you have a person that walks along a straight path at a speed of 4 feet per second, and there's a searchlight that's located on the ground 20 feet from the path, and is kept focused on the person and man. At what rate is the searchlight rotating when the man is 15 feet from the point in the path closest to the searchlight? Okay, so there's a lot of words there, right? So let's just start with the first sentence. A lot of these is just like reading comprehension and setting things up. Okay, walking along a straight path at a speed of 4 feet per second. Okay, someone give me a math word for that. We'll build the picture as we define things. Yeah, velocity. So let's call it, I don't know, what letter do you want to use? Let's say B. dB dt. And is this a fixed rate? Is this a changing rate? Do we not know what the derivative is? Do we always know the derivative is? It's fixed. Okay, so let's draw this. So we have a straight path and a person walking at 4 feet per second. Okay, so now let's use next clause. Next sentence. A searchlight is located on the ground 20 feet from the path and is kept focused. Okay, so if this is the path, what it means 20 feet from the path is that here's 20 feet, and here is a searchlight. Yeah, let's make it a smaller searchlight. And as man is walking through time, it's keeping focused on man. Okay, everyone agree that that picture emulates that sentence? So this is in time, right? So there's a motion here. And this is rotating. Questions about that one? Just the picture? Okay. At what rate is the searchlight rotating? What math word is that? So yes, DDT always, I know I'm saying this over and over. The big question here is what is changing? So the searchlight is fixed up here, but it's just rotating. So it's fixed at that point, 20 feet away. Oh, okay. So can you use a different word than position? Like, how would you describe the position? So, like where it's pointing, is that what you mean? Okay, good. Yeah, so what's another word for, how do you describe that motion? It's fixed, but it points in a different way as time increases. How could you describe a change? Like, what is the thing that's changing? What is rotation? What is changing in a rotation? Degree, yeah, so like angle. So for future reasons, we can let the angle be this angle. So over time, this angle is decreasing. So that's the rotation. Okay, so now the question is, at what rate is this rotating when man is 15 feet from the point in the path closest to the searchlight? So that's this point is the path closest to the searchlight. Okay, so I think what's helpful for this question is to draw stages in time. So if this is the angle that's changing, and this is the person, that's one stage in time. This is another stage in time. And what do we care about is the stage in time where this is 15, and we want to know what this is. Okay, so do we know, so these are right triangles, right? Do we know anything that's fixed between all these triangles? The y, yeah. So this value is always 20 because the searchlight isn't changing like in spatial position. But what is changing? This angle is changing. Okay, so big question. Do we know a formula? Oh, what else is changing? The angle is changing, and what else is changing? One other thing is changing here. Yes, the x component, right? This value is changing. Okay, do we know a formula that relates the sides of a right triangle and the angle? Right, these are the three pieces of information that we know, at least that we care about: the angle and the two sides. What formula can help us? You don't have to go straight to arctan, but the right idea. Just tan. Tan of theta is what? So theta would be arctan, but we can just work with tan. We don't need arctan. So let this be like b or something. Yeah, x over y. So it would be b over, but this is always 20, right? Yeah, so now take the derivative. What's the derivative of tangent of theta? Oh, so we should put some t's here, right? So we don't get confused. So what's the derivative of tangent of theta of t? So we know this one already, so I'll do it because we're running out of time. It's secant squared of theta of t, and then d theta dt, right, by the chain rule. And this one is db dt times 1 over 20. Okay, db dt was fixed to be 4. So the question is secant squared of theta of t, d theta dt is equal to 1/5. So the question was, how is the angle changing when the person is 15 feet away from that point? Do you know what secant squared of theta is? How do you find secant? Forget about the squared. How do you find secant of theta? Yeah, it's 1 over cosine, and then how do you find cosine of theta? That's cotangent. Yeah, hypotenuse. We need to know this, right? So this is square root of. That's okay. Yeah, it's late. Square root of 15 squared plus 20 squared. So what is so cosine is we 20 over that. So secant theta is square root of 15 squared plus 20 squared over 20. So secant squared is 15 squared plus 20 squared over 20 squared. So I'm sure that simplifies to something a bit nicer. So we get 15 squared plus 20 squared over 20 squared. D theta dt is equal to 1/5. So we have d theta dt is 20 squared over 5 times 1 over 15 squared plus 20 squared. All right. I don't know. Is this a nice number? 15 squared plus 20 squared? What's this? Mm-hmm. 625. That is actually nice. Okay, and then I'm sure that we can simplify that. Okay, cool. Okay, questions. So I think the hardest part was just, oh, the square root of that is 625? Okay. This is 3125. So what would the units be? Be radians. No, it's fine. Whatever it is. If it could be 15 squared plus 20 squared. That's fine. All right. Sorry I went over a little bit, but just wanted to get that problem. So I'll stop recording now.